Good afternoon everyone, has Techno20 with you today for a tutorial about step-by-step electronics. We will cover in this tutorial most of the idea of conception, realization, and maybe with microcontroller programming, but for today we will just have a basic knowledge about electronics and numeral basis. So let's get started. For today we will just make an introduction of computing systems, what cover coding basis, logical operation and symbols, logic gates and simple circuits, internal organization of a computer, and in the end will be just a small summary and maybe an evaluation. Nowadays everyone use electronic things as daily basis utilities, but when you look at it, it's like magic with pieces, but in fact they're all made by human beings. You just maybe when you open something like a microwave, like a radio, even a small child toy, you just see lines, components, and what all these things are. But one thing is certain, it's just a big board with switches on or off. That's it. Just how to make it, or just to how it works. So maybe we'll get to that in the future, but for now we will see about coding basis. So in this section we will be manipulating three numeric coding, as we know, binary, decimal and hexadecimal. We will see how to pass from one to another, to make additions and subtractions. So we will be seeing a lot of those inscriptions, 25, 10 like index. But what you mean by that index is the numeric base. Like for example, we make when index is 10, that means a decimal, but the index is 16, that means a hexadecimal, that means base 16, and when it's 2, it's binary. First we will start with conversion between bases. We will take a random number. For example, we will take 37 as decimal. We will try to convert it to binary. So let's see how to do that. It's a simple calculation. You only need to make a division by 2 for every result until we will find as a result of quotient 0. as we see here, we start with 37 divided by 2, it's 18, and we'll rest 1. We'll just put it there, and that rest, it's LSB of our binary combination. LSB, what is that? That when it's like the unit in decimal, and as we go forth, the significance of the byte grow up. So LSB means abbreviation of least significant byte. Bit, not byte. So it's less significant bit. So we come back at our calculation. 18 divided by 2, 9, and we don't have any rest. 9 divided by 2 is 4 and rest 1. 4 divided by 2 is 2, rest 0. 2 divided by 2 is 1, rest 0. And 1 divided by 2, we find the 0, and the rest will be 1. And 1 will be like the most significant bit. So as a result, so 37 decimal will be 100101 in binary. I guess this transaction is simple so far. Well, we will continue with the same number, but now we will pass from binary to hexadecimal. It's just simple to make it. We need to divide the sequence, but starting from the right. We take 4 bits every sequence, like as we say here. So we start from the right, we take 4 bytes, and the rest will be 10 space 0 1 0 1. Let's see that what will give us. We have here the combination table as binary and how will be in hexadecimal. So we will see here 0 0 1 0 is 2 and 0 1 0 1 is 5, so will be 25 hexadecimal. So as we started 37 decimal, we find that combination in binary and will be 25 in hexadecimal. And now to continue the cycle, we will come back again at decimal from binary. So we say that the last one is the least significant bit. So as we say, that mean is 2 power 0, and as we go in the left, the power will grow up. To make the conversion between binary and decimal, it's really too easy. Just you need to make multiplication as shown here. Take it from which side you want. Just make it in order. We start from the most significant bit. So will be 1 multiplied by 2 power 5 plus 0 multiplied by 2 power 4 plus 0 multiplied by 2 power 3 plus 1 multiplied by 2 power 2 plus 0 multiplied by 2 power 1 plus 1 multiplied by 2 power 0. We will find first one is 32 plus 0 plus 0 plus 4 plus 0 plus 1. That will make 37. It's not that hard, just a small calculation. And we pass now at the logic operation and symbols. We'll start with additions for binary. As we know, binary is a base 2 numeric code, and that means only have 2 digits, 0 and 1. In binary, this combination, what is 13 in decimal plus 9 in decimal. So we'll make a simple calculation. 1 plus 1, as we say, will be 10 in binary. So 0, and we remain 1. 1 plus 0 is 1. 1 plus 0 is 1. And 1 plus 1 will be 10. So this operation will give us the result of 10110, what is 22 in decimal. But for subtraction, we need to pass through a transit situation, what is called the second complement. The second complement is an easy operation to make. You only need to invert the sequence, as the example show here. Ones become zeros and 0 become ones, and what you will find is called first complement. And to find the second complement, you just need to add 1 for the result, for the first complement. And when you have a subtraction, the second number you have to transform it in the second complement, and you will change the sign of the operation. Instead of minus will be plus. That's how you will make the subtraction in binary. And for hexadecimal numbers, we'll just take it as decimal, but we need, if it's more than 16, we need to find the difference and to carry with 1, like as we see here. Is 9 plus 14 will be 23. We take from it 16, will remain 7. And 1 pass to the second operation. That's why we have the 1. 1 plus 13 plus 11. 13 is D, B, D in hexadecimal, and 11 is B in hexadecimal. Will give us 25. 25 we take 7, we find 9, and we have a carry. Again we put it in the next one. It's 1 plus 3 plus 4, we find 8. And the last one will be 2 plus 9 is less than 15, so we find 11, what is B. So the result will be B897. Let's see about the subtraction. But in the subtraction, if the second digit is greater than the first, we will not take 1 from the next digit, but we will take 16, because it's base 16 numeric code, as shown here. F minus 8. Okay, F is 15, so we can make the operation. But in the next one, we have 9 and b. b is 11. But we cannot make the operation, so we take 16 from the next one, as shown here. 11 from 25, that means it's 9 plus 16 is 14. That means a in hexadecimal. And 2 from 4. 4 what? 4 because we take 1 from the 5. As shown here will be 2. So the result is given 2a7. Now we will see some symbols that we will use it in the future. Okay. This is the logic comparator, and is to verify that a condition or like two states are need to be true to can have a true result. It will be shown as the AND symbol, but the first part is the programming symbol and the second part is the writing symbol, double AND or a point, or as it say, it's like sequence or a result or the other is used as two straight bars or a plus. Inverter is an exclamation point or a slash, as we will see. And here we have the symbols of the gates, what we will use in electronic circuits. So we have the and here the result what give. So we'll give a true state only when both conditions are true, or will be true only if one of the condition is true. The NAND is the opposite of the AND. It will be true whatever it is only when both conditions are true, will give us a 0. The NOR is the inverse of the OR, not OR or not AND. XOR, it's a bit complicated, this one, because you need to make a bit of operation. Or you can say like this: we'll give you 1 when either 1 is true and when 1 is false, but when both are the same state, we'll give you 0. We'll give you 1 only when both sides have different state, like what we see here. 1 is 0, 1 is 1. We'll give you 1, but when are the same state, we'll give always 0. Or you can use this equation. It's not E and B, or A and not B. Or another operation will be A or B and not A or not B. You can use also those equations. And we have the buffer and the inverter. The inverter is just invert the state. If it's 0 will become 1, if it's 1 will become 0. The buffer is just like a trigger or switch, the same, will maintain the state If is 0 will be 0, if is 1 will stay 1. We will be using those symbols and gate in the next lesson, what is logic gate and simple circuits. The circuits is logic gate circuits. It's a combination of different gates to verify a condition of an output. What that means? To have a condition to verify the output. When you want to have a condition for the output, you put a series of operations to pass through to can verify that output. We will see this example to explain more. We have 3 input here, and the output is Q, but we need to verify the condition what we have it before. Let's take it step by step. So we have A and B, the first layer, and B or C, and B and C. So we will have those 3 results for the moment. The second one will be, so we have the first result, what is A and B, is straight to the last gate. That means will remain the same. But the second part, we still have one gate, what is the second layer, what have B or C and BC, what give us in the as a result B and C and B or C. And in the end, as final result, the output Q will be equal at A and B or B and C and B or C. Let's check that small table as shown here. So the output Q will be active only in the condition where are colored with green, but give a positive exit. So, or we have the combination 0 for C, active for B and active for A, or active for C, active for B and not 0 for A, or all 3 are active. And I guess this is all about the simple circuit gates. And for now we will go to see what is inside the computer, because we will be is almost the similar what we will see in the future, what is microcontrollers programming. So as we see here, the computer brain, the CPU, is the control process unit, have 3 buses. What are the main buses? Which are address bus, control bus and data bus. What is connected to most of all the peripherals of the computer and the internal memory. And as we see here, some are input but only go inside, some are outputs, that means to give a result, and some are input and output, like the hard disk, like the RAM. So we will explain the role of the address bus. The address bus is for internal address for the peripheral, as RAM, as the ROM, or the printer or the disk, all have internal addresses. So the first one is to specify where the information will go in that peripheral. What is the important one? The second one is the control bus. The control bus allow the CPU to enable the device what will receive the informations, or as we say it, information, to save it in that peripheral or to show it. And this is in general what is happening inside the computer. And in the end, just small notice or observation, and also maybe you will find small exercise or evaluation in the description. And thank you for your interest, and we will see you next chapter. Have a good day.